Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing an important type of organometallic compounds, particularly the transition metal diolefin complexes. And we have been discussing this transition metal diolefin complex in the pretext of the transition metal olefin complex. And what we had seen that these transition metal diolefin complex differ significantly from the transition metal olefin complex when this diolefin is conjugated. And in terms of the diolefin being conjugated, they have delocalized molecular orbitals, which results in lengthening or shortening of certain CC bonds of the diolefin moiety. As an example, what we had seen that for butadiene complex, when butadiene is bound to the metal, the change in the terminal as well as the terminal bonds and the CC internal bonds change upon coordination to the metal, and this can be sort of explained by the reaction that if there is a free butadiene, there is, and when that reacts with a metal to give a metal coordinated beta butadiene, the internal as well as the terminal bond lengths change. And what we had discussed in the last lecture is that we see similar change when light is induced, whereby the butadiene which is formed is excited. One of the electron gets excited, and there also we saw that there is similar change in the CC internal as well as terminal bond lengths. So, this was an interesting phenomenon which we discussed and was explained by the butadiene molecular orbital formed from the 4 pi type orbitals. So, what we had seen is that butadiene when it is activated by light or by metal show change in the bond lengths, which can be the terminal and internal, and these two changes are similar with regard to coordination to metal as well as by light excitation. And all of these could be explained by the p orbitals, p type orbitals of butadiene, which are responsible for the various kind of molecular orbitals, and that we had seen that these gives rise to psi 1, psi 2, psi 3 and psi 4, depending on the number of nodes that they combine to form after linear combination, and that the population of one or the depopulation of other would result or explain this change in the internal as well as terminal bond length. Now, with that in mind, let us take a look at some of the examples where similar change can be observed. For example, the influence of transition metal coordination on butadiene on the intra-ligand bond length of butadiene can be seen this is the free butadiene. The terminal bonds are 136 picometer, the internal is 145 picometer, So, internal is a longer bond, terminal is a shorter bond, but when it coordinates to metal, particularly zirconium BCP, then the terminal bond length, depending on the population and depopulation, the extent of forward sigma and pi back donation occur, the terminal bond has increased to about 145 picometer, and the internal one has shortened to about 140 picometer. And the same can be seen from iron coordination, where butadiene when coordinated to FeCO3, the terminal one is 146 and the internal one is 146. So, there is a significant change, the interligand bond length changes as the metal coordination occurs, and also it depends on the nature of the metal. For example, iron is more electron rich metal than zirconium, and obviously the extent of the interactions in these two metals would be different. And these binding of butadiene to the metal can be characterized by various NMR techniques. For example, this can be done by carbon NMR, provides a useful tool, is certainly useful for characterizing the binding of butadiene to the metal complexes, and the carbon 13 coupling constant is far more useful in ascertaining this binding to the metal. For example, in eta 4,1,3 butadiene, so this is one type of binding. Now, it has a canonical form which is where the olefinic bond is binding. Now, if in this structure the terminal bonds are sp3 types, and in this structure the terminal bond is sp2 types and can be differentiated using 13C NMR. Also, there is the late transition metal designated as pi complex, whereas the early transition metal designated as metallocyclopentanes. So, this structure is called metallocyclopentene, similar to the metallocyclopropene that we had seen. These are called metallocyclopentene. And this is just called simply pi complex. So, late transition metal designated as pi complex, whereas early transition metal designated as metallocyclopentane. pentene. So, this is a interesting feature which can distinguish between these late transition metal type of canonical structure that exists with the late transition metal as well as the early transition metal, and that the hybridization of the ligand would change on going from this metallocyclopentene intermediate onto the simple pi complex of the type shown. So, next we come to an interesting topic which are moving over from olefin complexes. These are transition metal alkyne complexes. So, the main aspects of transition metal alkyne complexes are cyclo-oligomerization reactions of alkyne as well as a variety of products formed in the reaction between alkyne and the transition metal carbonyl complexes. So, they are important in terms of their utility for a kind of oligomerization reactions that go, which are common for alkyne. So, it is important for us to give this class of compounds special treatment, particularly looking into the synthesis reactivity and the property as well as bonding studies of transition metal alkyne complexes. Now, as for the transition metal alkynes to exhibit different coordination modes, and these can be monodentate, where the alkyne is bound to the metal. So, this is called monodentate. It can be bidentate, it can be bidentate with a pi bond, it can be bridging, it can be tridentate, or it can even be tetradentate. So, this is bidentate, again bidentate, tridentate and tetradentate, of which these two are simple 2 electron donor and these are 4 electron donor, and when it binds as a 2 electron donors, then the metal fragment M is electron rich, and when it binds as 4, then the metal electron fragments is electron poor. So, these slide throws very good insight as to the versatility of the alkyne as a ligand. How does it bind on a side on fashion? It can be monodentate, bidentate. It has different modes of coordination to the metal. It can bind to metal with a single metal, double metal or a triple metal, as well as it can give 2 electrons and 4 electron donors, depending on whether the metal is a electron rich or a electron deficient center. Now, these being very important compounds in terms of their catalytic utility, and also we have looked at the rich binding mode that it offers. We are going to look at the preparations of some of these transition metal alkyne complexes. Preparations, and the first and the foremost is preparation by substitution reaction. This is Na2 PtCl4 reacting with TBu2C2 in ethanol and RNH2, provided this PtCl in H2R and acetylene C T-butyl T-butyl. Now, this bond is 124 picometer and this angle is deviated from linearity and it is 165 degrees. The CC stretch nu CC can also be characterized by IR, and that is 28 centimeter inverse. So, this is a method where the chlorides have been substituted by alkyne, providing this alkyne complex. There are other examples of the substitution reactions. For example, the reaction of Cp2 titanium carbonyl compound plus alkyne in heptane under vacuum 25 degrees centigrade 3-hour eliminate CO to give this Cp titanium CO C phenyl compound, where this angle now is more distorted to 146 degree and this distance is 128 picometer. So, this has also been characterized by IR, where nu CC stretch is even 1780 centimeter inverse. Now, there is another preparation by substitution reaction. Triphenyl phosphane giving this alkyne complex with this phenyl and 2 of this triphenyl phosphane has a degree of 140 degree, which is also different from linearity, and 132 picometer. This has also been characterized by IR, where it is 1750 centimeter inverse. So, with that, let me conclude the topics that has been discussed in this lecture. We have looked into these transition metal diolefin complexes to begin with, and looked at some of the changes of the internal as well as terminal bond lengths that happens when they coordinate to transition metal. and then we began the transition metal alkyne complexes. We have looked, we have also studied as to why these complexes are so important in organometallic chemistry. We have also looked at how these complexes bind to the transition metal in terms of their behaving as a monodentate bidentate. They show a versatile binding mode on going from mononuclear, binuclear and as well as tetranuclear. They also, in terms of electron donation, they show 2 electron as well as 4 electron donating abilities depending on the electron richness of the metal. And then we looked into few synthetic methods that are available for preparing these transition metal alkyne complexes, which mainly the ones that we have looked at are mainly by substitution reaction. So, with that I am going to conclude today's lecture, and I thank you for being with me in this lecture, and I look forward to being with you in next lecture, where we are going to take up these transition metal alkyne complexes in much more detail. With that, let me conclude today's lecture and look forward to being with you in the next lecture. Till then, thank you and goodbye.